So, here's where we're going to start tonight. Not with a fact, not with a definition, with a promise, really, which is that we are about to begin moving, and once we start, we are not going to stop. We're going to begin somewhere smaller than you can picture, smaller than a single letter on this page would be if you could somehow shrink down and stand beside it. And we're going to pull back, and back, and back, past everything you know, past the room you're lying in, past the sky, past the sun, past the edge of everything the eye has ever seen, until we reach a scale so large that the word large stops meaning anything useful at all. That's the whole shape of tonight. One long exhale outward. No stops along the way that feel like new chapters, no doors closing behind us, just motion. The same way a camera might pull back from a single freckle on someone's arm until, without any cuts, without any jumps, you're looking at the whole person, then the room, then the city, then the curve of the planet from orbit. Except we're going to go so much farther than that. So settle in. Get comfortable. Let your eyes close if they haven't already. There's nowhere to be and nothing to remember. If you drift off in the first 2 minutes, that's completely fine. The Zoom will still be here waiting whenever you surface again. And honestly, half of what we're about to talk about makes more intuitive sense to a half-asleep mind than a fully alert one, because a lot of it doesn't want to be understood in tidy little boxes. It wants to be felt, the way you feel the size of a cathedral by standing under it rather than by reading its dimensions off a plaque. So let's go all the way down first. Before we can pull back, we have to start at the bottom, and the bottom, for tonight's purposes, is the inside of a single atom, a thing so small that if you tried to picture it next to a grain of sand, the grain of sand would tower over it the way a mountain range towers over a single ant. And I don't just mean small the way a pebble is small compared to a house. I mean small in a way that breaks your normal sense of scale entirely, because you could line up something like 100 million atoms in a row and the line would only stretch about a centimeter, roughly the width of your fingernail. 100 million. Try to hold that number gently in your mind for a second, and then just let it go, because you don't need to keep holding it. You just need to feel the shape of it, the way it dwarfs anything you're used to counting. Now, at the center of that unbelievably tiny atom sits something even tinier still, a nucleus, a dense little knot of protons and neutrons, and it carries a positive electrical charge, sitting there quietly like the sun at the center of a solar system. And further out, much further out in relative terms, there are electrons, tiny charged particles that don't sit still, that exist in a kind of restless orbit around that nucleus, held there by the pull between opposite charges, the same basic attraction that makes a balloon stick to a wall after you rub it on your hair. Opposite charges pull toward each other. That's not a complicated idea. It's almost the first thing you learn about electricity as a kid, without necessarily calling it that. And already, right here, at the very smallest scale we're ever going to visit tonight, there's something worth just noticing quietly before we go any further. That nucleus, and the electrons drifting around it, aren't actually sitting in stillness the way a drawing in a textbook might make them look, two neat little dots connected by a tidy circular line. Everything down here is in constant motion, constant vibration, constant faint trembling, even in matter that looks, from any distance larger than an atom, perfectly calm and perfectly solid. The stillness you feel in a tabletop, or in your own hand resting against the blanket right now, is really just an enormous, patient average of an almost uncountable number of tiny, restless, ceaseless movements happening far too fast and far too small for you to ever sense directly. It's a bit like looking down at a calm lake from a great height and assuming the water isn't moving at all, when really, if you got close enough, you'd find it full of countless small currents and ripples, all canceling out into what looks, from a distance, like perfect, glassy stillness. Here's the part one want you to sit with for a while, though, because it's the actual heart of everything we're going to talk about tonight, long before we ever get around to using any particular word for it. Think of an electron the way you might think of a satellite orbiting the Earth. A satellite in a nice stable orbit is basically falling toward the Earth constantly, except it's moving sideways fast enough that its fall curves around the planet instead of crashing into it. It's caught in a kind of permanent, graceful compromise between falling and escaping. And an electron around a nucleus is doing something conceptually similar, held in place by the pull of that opposite charge, existing in a kind of stable, quiet equilibrium. But now imagine giving that satellite a sudden burst of extra speed. Push it hard enough, and it stops being caught in that graceful compromise. It stops falling around the planet, and instead it just leaves. It breaks free of the gravity that was holding it in orbit and sails off into open space. And it doesn't come back unless something out there catches it again. That's the image I want you to hold on to, gently, without gripping it too hard, because that's essentially what's happening to an electron when you give it enough energy. Enough heat, enough of a jolt, enough of a shove, and an electron that was orbiting quietly around its atom simply leaves. It breaks free of the pull that was holding it there, and it goes sailing off into whatever surrounds it, no longer bound to that particular nucleus at all. There's a word for how tightly an electron is held onto by its atom, and it's called binding energy, which is really just a fancy way of saying how much of a shove it takes to knock that electron loose. Every electron in every atom has its own particular binding energy, its own particular threshold, and below that threshold, nothing happens. The electron just orbits along peacefully, unbothered, doing whatever electrons do. But once you cross that threshold, once you deliver enough energy, that binding just gives way. The same way a rope holding a boat to a dock gives way once the current pulling on the boat gets strong enough. Right up until that point, the rope holds. And then, all at once, it doesn't. And when that happens, when an electron gets stripped away from its atom, you're left with two things where there used to be one calm, neutral atom. You're left with the electron itself, now drifting free, negatively charged and unattached. And you're left with what remains of the original atom, which is now missing a piece of its negative charge, which means it's no longer neutral. It's carrying a positive charge now, because it's lost one of the negative electrons that used to balance out the positive charge sitting in its nucleus. This leftover, charged husk of an atom has a name too. It's called an ion. And this whole process, the stripping away of an electron, the creation of that charged remainder, has a name of its own. It's called ionization. I want to slow down right here, because this is really the whole secret of the entire night. The seed that everything else is going to grow out of, and I don't want to rush past it just because the vocabulary sounds technical. Ionization is just this. Something ordinary, some collection of atoms sitting there quietly, minding their own business, gets hit with enough energy that electrons start getting torn loose from their nuclei. That's it. That's the entire idea. It's not exotic. It's not something that only happens in a laboratory behind thick glass. It's one of the most common transformations in the entire universe, and once it happens to a large enough number of atoms all at once, something strange and beautiful starts to occur. You stop having a simple collection of neutral atoms bumping into each other. You start having a churning sea of loose electrons and charged ions, all tangled together, all responding to each other's electric fields, all pushing and pulling on one another in ways that neutral atoms never do. It starts behaving like something new, something that isn't quite a gas anymore in the way you'd normally picture a gas, all lazy and uninvolved with itself, and isn't a liquid, and isn't a solid. Think about what happens to those loose electrons and those newly charged ions once they're set free like that. In an ordinary gas, atoms are basically indifferent to each other. They collide occasionally, they bounce off one another, but for the most part, each atom is its own tiny isolated world, electrically neutral, uninterested in its neighbors. But once you've ionized a chunk of that gas, once you've knocked electrons loose and left charged ions behind, suddenly every single particle in there is electrically sensitive to every other particle around it. The negative electrons feel the pull of the positive ions. The positive ions feel the pull of the negative electrons. Push one of them, and it doesn't just move on its own. It drags a whole invisible web of electric influence along with it. And that web tugs on its neighbors, and they tug on their neighbors, all the way through the whole collection of particles. It behaves collectively in a way ordinary neutral gas simply does not. This is worth just sitting inside of for a moment, without needing to do anything with it yet. A regular gas is like a crowd of strangers standing quietly in an empty field, each person minding their own business, occasionally bumping into someone nearby, but otherwise entirely independent. This new, ionized version is like that same crowd, except now everyone is holding hands, invisibly, through electric and magnetic force, so that if one person sways, the whole crowd sways with them, a ripple moving through the entire group at once. That collective, electrically wired behavior is the whole reason this stuff acts so differently from ordinary matter, and it's the whole reason it eventually earned itself its own name, its own category, separate from solid, liquid, and gas. We're not there yet, though. We're going to sit with this nameless, nascent thing a little longer before we give it a label, the same way you might sit with a feeling for a while before you find the right word for it. It doesn't take a dramatic amount of energy to do this, by the way, which is part of why it happens so constantly, so casually, all throughout the universe, rather than being some rare and difficult thing to arrange. For the outermost, most loosely held electron in a typical atom, it might only take an amount of energy so small that physicists measure it in units called electron volts, a handful of them, sometimes even less than a handful, which is a tiny, almost trivial quantity of energy by the standards of the physical world. A little bit of heat, a little bit of friction, a little bit of electric field concentrated in the right place. That's often all it takes to tip an electron over the edge of that binding threshold and send it drifting free. It's a bit like the difference between a book resting flat on a table and the same book balanced right on the very edge of that table. It takes almost nothing, the faintest nudge, to send it tipping over into a fall, even though a moment earlier it looked perfectly stable sitting there. Atoms and their electrons are often poised in exactly the kind of precarious, easily tipped balance, which is part of why ionization turns out to be so wonderfully common rather than some rare and exotic event reserved for extreme laboratory conditions. So, if you're already drifting a little, that's completely fine. Nothing about what comes next requires you to have followed every piece of that. The important thing to carry forward, half-consciously if that's where you are right now, is just this one small, strange fact. Give ordinary matter enough energy, and its electrons start breaking loose from their atoms, and what's left behaves like nothing you've encountered before, a crowd of charged particles all electrically entangled with each other, all swaying together. Hold that loosely, like a stone you're carrying in your coat pocket rather than gripping in your fist, and let's start to pull back now, slowly, gently, out of this impossibly tiny world and into something you can actually picture with your eyes closed. There's no need to rush that transition either. We have a very long way to travel tonight, and the whole point of moving this slowly is to let each new scale arrive on its own, quietly, the way a shape emerges out of fog only once you've walked close enough to it, rather than being announced all at once from a distance. So picture something small and warm and completely familiar. A candle flame. Maybe there's actually one somewhere near you right now. Or maybe there isn't, but you know exactly what one looks like, that soft orange teardrop of light, flickering just slightly even in a still room, casting a small warm circle onto whatever surface it's sitting on. You've probably watched a candle flame 1,000 times in your life without ever once wondering what it actually is, and that's completely understandable, because it looks so simple. It looks like nothing more than light and a bit of heat, a small domesticated bit of fire doing exactly what fire has always done since long before anyone could explain it. But here's what's actually happening inside that little orange glow, and it connects directly, without any gap at all, to everything we just spent time with a moment ago. A candle flame is hot. Genuinely, seriously hot. Hot enough that the gases swirling around inside it, the vaporized wax, the oxygen being pulled in from the surrounding air, are being agitated with enough energy that some fraction of their atoms are getting knocked apart in exactly the way we just talked about. Electrons are getting stripped loose from their orbits. Ions are being left behind. It's not happening to every single atom in there, and it's not happening with nearly the intensity that we're eventually going to encounter as we keep pulling back tonight. But it is happening, right there, an inch or two above the wick, in that soft, familiar, orange light that's been sitting on birthday cakes and dinner tables for as long as anyone alive has been alive. That candle flame, that gentle, flickering thing you've probably never given a second thought to, is a weakly ionized plasma. And there it is. That's the word. I've been holding it back this whole time on purpose, the same way you might hold back a punchline, because I wanted you to feel the phenomenon first, to sit inside the strangeness of ionization before we ever hung a label on it. The same way it's often more useful to actually feel an emotion for a while before you rush to name it. But now you have the word, and once you have it, you start noticing that this same phenomenon, this same electrically charged, collectively behaving state of matter, is everywhere. It is not some exotic substance locked away in a research facility somewhere. It's flickering gently a few inches above a birthday candle. It's been doing that at every birthday party you've ever attended. A man named Irving Langmuir, working at General Electric back in the 1920s, was the one who actually needed a word for this stuff. And the story of how he landed on it is a nice, small human detail worth folding in here. Briefly, the way you'd mention a friend's name in passing rather than launching into their whole biography. Langmuir was studying the behavior of ionized gases inside electrical discharge tubes, watching how they moved and pulsed and organized themselves, and something about the way this charged, churning material behaved reminded him of blood plasma, that pale, carrying fluid that ferries blood cells around your body. Just as blood plasma carries red and white blood cells suspended within it, this ionized gas seemed to carry its charged particles around in its own kind of collective, fluid-like medium. So he borrowed the word, plasma, and it stuck, the way a good nickname sticks, becoming the permanent name for what is often called the fourth state of matter, sitting there alongside solid, liquid, and gas, except stranger and, as it turns out, vastly more common throughout the universe than any of the other three. It's worth just noticing, gently, what a small and human moment that naming was. A scientist in a lab in the 1920s, staring at a glowing tube, reaching for a word that felt right, borrowing it from an entirely different field of study, medicine, of all things, because the shape of the phenomenon reminded him of something else he already knew. That's how a lot of scientific language actually gets born, not through some grand committee deciding on the perfect Latin root, but through someone noticing a resemblance and just going with it. And now, a century later, that borrowed word covers everything from the flame on your stove to the interior of the sun to the space between galaxies. Not bad, for a word that started as a passing comparison to blood. So think again about that candle flame, sitting there quietly on a table, that soft, familiar orange glow. Inside it, atoms are being torn apart and put back together constantly, electrons breaking loose, ions forming, light being given off as electrons occasionally fall back into orbits and release a little burst of energy on their way down. It's chaotic and violent at the scale of individual atoms, and yet from where you're sitting, it just looks like a gentle, calm little flame, flickering softly, giving off warmth and light in a way that feels almost cozy rather than dangerous. That's a strange and lovely thing to notice, that something so wild at the atomic scale can look so peaceful from a few feet away. It's a bit like how the ocean looks calm and glassy from a cliff top, even while it's full of enormous churning currents underneath the surface. A gas stove burner is doing the same thing, that ring of blue flame you might have watched heating a pot of water. It's a slightly hotter, more energetic version of the same story, more of the gas getting ionized, more electrons breaking loose, which is part of why that flame burns blue instead of orange, the different temperature and different chemistry, changing exactly which colors of light get released as electrons settle back into place. A struck match, that little flare of light at the tip when you drag it across the rough strip of a matchbox, is the same story again, compressed into a single brief burst. Every one of these small, ordinary household flames is a weakly ionized plasma, doing on your kitchen counter, at a tiny, tame scale, the same fundamental thing that's happening at towering, ferocious scales we haven't gotten to yet. And once you start looking for this phenomenon at this particular size, you find it in other places too, not just in open flame. Think about a neon sign, one of those glowing tubes of colored light you might see in the window of an old diner or a bar, spelling out a word in that particular buzzing, saturated glow that neon signs have. Inside that glass tube, there's a small amount of gas, often neon itself, though other gases produce other colors, sealed inside at low pressure, and there are electrodes at either end of the tube that apply an electric voltage across the gas. That voltage does exactly what heat did inside the candle flame. It rips electrons loose from the neon atoms, ionizes the gas inside the tube, and as those freed electrons eventually recombine with the ions, falling back into orbit, they release their extra energy as light, in neon's case, a very particular warm red-orange glow. A French engineer named Georges Claude was the one who actually turned this particular flavor of ionized gas into something commercially useful, showing off the very first neon tube lighting to the public in Paris in the very early 1910s. And within just a few years, these glowing glass tubes had spread across cities everywhere, bent into letters and shapes, hanging in windows, glowing softly through fog and rain in a way that ordinary filament bulbs of the era simply couldn't match. There's something rather sweet about that, too. A French engineer bending glass tubes filled with a rare gas, letting an electric current ionize it into that particular warm glow, and within a generation, entire city skylines were lit up at night with tiny, tamed fragments of the same phenomenon that splits the sky open during a thunderstorm. A fluorescent tube in an office ceiling is doing something quite similar, a sealed tube of mercury vapor being ionized by an electric current, giving off light. Though in that case the visible light you see is actually produced indirectly, through a phosphor coating on the inside of the glass that gets excited by the ultraviolet light the ionized mercury vapor is putting out. So there's this whole quiet category of human-made, human-engineered plasma sitting at roughly this same modest scale, the scale of a room, of a tabletop, of a glass tube you could hold in your hands. A candle flame, a gas burner, a struck match, a neon sign glowing in a window, a fluorescent tube humming softly overhead. None of them look particularly exotic. None of them announce themselves as belonging to some grand, universal category of matter. They just sit there, giving off their gentle light, doing this strange electrical dance of ionization and recombination over and over, thousands of times a second, invisible to the naked eye, hidden behind the calm, steady glow that's the only thing you ever actually perceive. It's worth noticing, too, just how many of the small glowing conveniences scattered through an ordinary evening actually belong to this same quiet family. The soft orange coil inside an old-fashioned space heater. The faint violet glow sometimes visible through the grill of certain electronic devices. The gentle hiss and flicker of a pilot light on an old stove, burning low and steady in the dark long after everyone in the house has gone to bed. None of these ask for your attention. None of them look like they belong to the same grand category as the sun or a lightning bolt. They just sit there, quietly doing their small domesticated version of ionization, over and over, the same electrons breaking loose and falling back into place, the same soft light leaking out as a byproduct of that endless tiny churn. It's a strange comfort, in its own way, to realize that this phenomenon has been keeping you gently lit and gently warm your entire life, tucked into the corners of ordinary rooms, never once needing to be noticed in order to keep doing its quiet work. If you're starting to feel your thoughts get looser and slower right now, that's completely fine, and honestly, it's a nice moment for it, because there's nothing more to hold on to right at this instant except a soft orange flicker and a word borrowed from blood. Let that sit there for a while if you want to. We're about to pull back further, out past this small tabletop scale, out past the walls of whatever room you're in, because there's a much bigger, wilder version of exactly this same phenomenon waiting for us in the sky itself. And it's the kind of thing that used to make entire ships' crews go quiet and start whispering prayers. Let's pull back now, out past the tabletop, out past the ceiling, out through the walls of wherever you happen to be lying, up into open sky, because there's a much larger, much wilder cousin of that candle flame waiting for us up there. One that everyone has seen, and almost no one thinks of the way we're about to think of it tonight. A lightning bolt. You know what lightning looks like. That sudden, jagged, impossibly bright crack of light tearing across a dark sky during a summer storm. There and gone in a fraction of a second, followed a few moments later by that low rolling boom of thunder. Most people experience lightning the way they experience a magic trick, as something that just happens, fast and bright, and a little frightening, without much curiosity about the actual mechanism underneath. But the mechanism is worth slowing down for, because it's the exact same story we've been telling all along, just turned up to a staggering, room-filling, sky-splitting intensity. Here's roughly how it unfolds. Inside a thundercloud, tiny ice crystals and water droplets are constantly colliding with each other, jostled around by powerful updrafts and downdrafts. And all that friction and collision starts separating electric charge, the same basic way rubbing a balloon on your hair separates charge, except happening over and over, billions of times, throughout an enormous churning cloud. Negative charge tends to accumulate low down in the cloud, positive charge tends to build up higher, and eventually the imbalance becomes so extreme, the electric field so intense, that the air itself, which normally acts as a stubborn insulator, simply cannot hold back the imbalance any longer. And when that happens, a faint, branching tendril of ionized air, called a step leader, begins creeping downward from the cloud, invisible to your eye, feeling its way toward the ground in short, jagged, hesitant steps, pausing and branching, and choosing a path the way water finds its way downhill through a landscape, taking whatever route offers the least resistance. As that step leader approaches the ground, an answering streamer often rises up to meet it, from a tree, from a building, sometimes from a person standing in an open field, and when the two connect, you get a channel of highly ionized air stretching from the cloud all the way down to the earth. And through that channel surges what's called the return stroke, an enormous flood of electric current racing back up from the ground into the cloud. And it's that return stroke that produces the blinding flash you actually see and the thunderclap you hear a few seconds later, once the sound has had time to catch up with the light. That channel of ionized air, that glowing conduit connecting sky to ground for the briefest instant, is plasma. The exact same phenomenon as the candle flame, electrons ripped loose from their atoms, ions left behind, the whole thing behaving as one electrically wired, collective entity, except this time the temperature inside that lightning channel can reach something like 30,000 Kelvin, briefly, for a few millionths of a second, hotter than the surface of the sun by a significant margin. Wait, let that sit there for a second. Hotter than the surface of the sun. A bolt of lightning, cracking across the sky above a backyard barbecue or a highway during a summer storm, is briefly hotter than the visible surface of the star that our entire planet orbits. That's the kind of fact that's worth just holding still with for a moment, turning it over, before we keep moving. There's a smaller, gentler, far less violent cousin of lightning that belongs at roughly this same scale, and it has one of those wonderful old names that sounds like it belongs in a sailor's diary, because it does. St. Elmo's fire. Sailors on ships for centuries described it, a strange, ghostly bluish or violet glow that would sometimes appear at the tips of a ship's masts during stormy weather, a quiet, hissing, softly luminous flame that didn't burn anything and didn't seem to be connected to any obvious fire. They named it after Saint Erasmus of Formia, a patron saint of sailors, taking it as a sign of protection, a small holy light appearing right when the weather turned most dangerous. For a very long time, nobody had any real scientific explanation for it at all. It was just a strange, beautiful, slightly eerie thing that happened sometimes, high up on a mast in the middle of a storm, and sailors simply learned to expect it and to take some comfort from it. What's actually happening is, once again, exactly the same underlying story. During a thunderstorm, the electric field in the air can become strong enough, especially around a pointed object like the tip of a ship's mast or the spire of a tall building, to ionize the air right at that point without ever producing a full lightning strike. The electric field concentrates itself at sharp points, the same reason a lightning rod works. And if that concentrated field gets strong enough, it ionizes the surrounding air just a little, just enough to produce a soft, continuous, hissing glow rather than one single violent discharge. It's the same electrical dance as lightning, but played gently, quietly, sustained rather than instantaneous, a small local plasma clinging to the tip of a mast instead of a whole channel connecting sky to earth. And while we're up here at this human scale, sky-sized on one end and just barely bigger than a person on the other, it's worth mentioning one more thing that belongs in this same grouping, because it's something humans learned to create on purpose rather than something we simply witnessed and wondered at. Plasma cutting and welding torches. If you've ever seen sparks flying in a metal workshop, a torch slicing cleanly through a thick steel plate, or a welder joining two pieces of metal together with a small, intensely bright, hissing flame, you've been looking at engineered, deliberately controlled plasma, created by forcing a gas through a narrow nozzle while passing an electric arc through it, ionizing that gas into a thin, incredibly hot jet capable of melting or even vaporizing metal on contact. It's the same fundamental phenomenon as the candle flame and the lightning bolt, electrons stripped loose, ions left behind, everything behaving collectively as one electrically active substance. Except here humans have learned to aim it, to control its temperature and its shape with real precision, turning a wild atmospheric phenomenon into a tool sitting on a workshop bench. It's worth pausing, too, on just how constant this particular phenomenon actually is, even though any single bolt only lasts a fraction of a second. Somewhere on this planet, right now, while you're lying there listening to this, a lightning bolt is very likely striking, and then another one a few seconds later, somewhere else, and another one after that, on and on. An estimated 40 or so flashes happening across the whole globe every single second of every single day, scattered mostly across the tropics, where warm, moist air keeps feeding thunderstorms almost continuously. Each one of those flashes is a fresh little channel of plasma, blazing brightly for a few millionths of a second and then vanishing completely, leaving no trace behind except a rumble of thunder rolling outward and a faint smell of ozone in the air nearby. It's a phenomenon that never actually stops happening anywhere on the planet, even in the dead of night. Even while you sleep, this same electrical dance flickering somewhere out there in the dark, over and over, quietly, relentlessly, the whole time. And that plasma-cutting torch we mentioned a moment ago, humming away on a workshop bench somewhere, deserves one more small memory before we move on, because it really is a lovely piece of engineering to picture clearly. A jet of gas, forced through a narrow nozzle, gets threaded through an electric arc right at the tip of the torch, and in that instant, the gas ionizes, becoming a thin, focused column of the exact same substance as a lightning bolt, except tamed now, aimed, held steady in a technician's gloved hand, hot enough to slice cleanly through a thick steel beam the way a warm knife slices through butter. It's a strange thought to sit with for a moment, that the same fundamental phenomenon capable of splitting open the sky during a summer storm can also be held quietly in one hand, pointed carefully, and used to build a bridge or a ship or the steel frame of a building. So here we are, still fairly close to home in the grand scheme of what's coming tonight. But already we've traveled from something smaller than the eye can see all the way up to something that spans the height of a thundercloud, and everywhere along the way, the same basic story keeps repeating itself, electrons torn loose, ions left behind, everything behaving as one collective, electrically wired substance. A candle flame on a table, a welding torch in a workshop, a crack of lightning splitting the summer sky, all of it the same underlying phenomenon, just wearing different scales and different costumes. If your thoughts are starting to loosen and drift again, that's exactly where they should be right now, because there's nothing urgent left to hold on to down here at the human scale. We've done what we came to do at this size. So let's keep pulling back, out past the clouds now, out past the point where thunderstorms even form, up into thinner and thinner air, because there's an entire permanent layer of this same phenomenon wrapped quietly around the whole planet. One that most people never think about at all, even though it's the reason a radio signal can travel around the curve of the Earth instead of shooting straight off into space. So let's keep moving outward, past the clouds now, past the altitude where even the tallest thunderstorms top out, up through air that's grown so thin it can barely be called air anymore, up into a region of the sky that doesn't have a dramatic, memorable name the way the ozone layer does, even though it deserves one just as much. This is the ionosphere, a vast, faint, permanently ionized layer wrapped all the way around the Earth, starting somewhere around 60 kilometers up and stretching out past 1,000 kilometers in places, sitting there quietly, all day and all night, every single day of the planet's existence. The ionosphere exists because sunlight, particularly the high-energy ultraviolet and X-ray light that never even makes it down to the surface where you're lying right now, slams into the thin atoms and molecules way up in the atmosphere with enough energy to knock electrons loose from them, ionizing that thin, high air the same way heat ionizes the gas inside a candle flame, the same way an electric field ionizes the air around a ship's mast. It's the same story again, just happening continuously, gently, across an entire spherical shell wrapped around the whole planet, sunlight doing the ionizing instead of heat or a direct electric field. And this permanent layer of charged particles turns out to do something wonderfully useful, almost by accident. Radio waves, when they hit that ionized layer, don't just pass straight through it the way they'd pass through ordinary neutral air. They bounce, the same way light bounces off a mirror, And that bouncing is the entire reason a radio signal broadcast from one side of the Earth can be picked up on the other side of a curved planet, skipping off this invisible ionized ceiling high above the ground the way a stone skips off the surface of a pond, hopping from ionosphere down to Earth and back up again, hop after hop, carrying its signal along the curve of the world. Now, tucked inside that same broad region of sky, sometimes lower, sometimes overlapping with it, there is something far more beautiful, far more famous, and far more emotionally overwhelming to actually witness with your own eyes than any invisible radio bouncing layer could ever be. The aurora. If you have ever seen the Northern Lights or the Southern Lights, it's far less talked about twin down near Antarctica. You already know that no photograph and no description really captures it properly. That shifting, rippling curtain of green and sometimes red and sometimes violet light, hanging and swaying across the night sky like something alive, like fabric moving in a wind you can't feel. Here's what's actually happening up there, and it connects, in a lovely and slightly dizzying way, all the way back to the sun itself, which we're going to visit properly a little further along tonight, but which deserves a first mention right now. The sun is constantly flinging off a stream of charged particles, mostly electrons and protons, in every direction, all the time, a kind of continuous exhalation that we're going to spend real time with later. Some of that stream reaches the Earth, and the Earth, luckily for everything living on it, has a magnetic field wrapped around it, generated deep down in its molten metallic core, and that magnetic field acts like an enormous invisible shield, deflecting most of that incoming charged material harmlessly around the planet. But not all of it. Some of those charged particles get funneled, caught and channeled by the shape of that magnetic field, down toward the planet's magnetic poles, the way a funnel guides water down toward a narrow spout, and they come slamming down into the thin upper atmosphere at exactly those high latitudes, up near the Arctic and Antarctic circles, where the magnetic field lines dive down toward the ground. When those incoming charged particles collide with the oxygen and nitrogen atoms sitting up there in the thin high air, they transfer their energy in exactly the same way we've been describing all along, knocking electrons loose in some cases, exciting them into higher energy states in others, and as those electrons eventually settle back down, they release that extra energy as light, at very particular colors depending on which atom got hit and at what altitude. Oxygen, when it's excited at around 100 kilometers up, tends to glow that signature eerie green, the color most people picture instantly when they hear the word aurora. Oxygen excited even higher up, out past 200 kilometers, tends to glow a deep, rarer red. And nitrogen, when it gets involved, tends to contribute blues and purples along the lower edges of the display, where the atmosphere is a little denser. So that whole shifting, rippling curtain of color you might have seen in photographs, or maybe seen with your own eyes if you've ever been lucky enough to stand under a clear sky at just the right latitude on just the right night, is a plasma phenomenon, precisely the same underlying story as the candle flame and the lightning bolt, just painted across the entire sky instead of confined to a tabletop or a single jagged channel of air. And this bouncing layer isn't actually a single uniform shell either, if you want to picture it a little more precisely. It's made of several distinct sublayers, stacked one above another at different altitudes, each one ionized to a different degree depending on how much sunlight reaches it and what kind of atoms happen to live at that particular height. And those layers shift and thin and thicken depending on the time of day, growing weaker after sunset as the ionizing sunlight disappears and the loose electrons slowly begin recombining with their ions in the dark, then strengthening again every morning as sunlight returns to knock them loose once more. That daily rhythm, invisible and silent, high overhead, is part of why certain radio stations that carry clearly across a whole country at night fade out again by the time the sun comes up, the whole delicate mirror rearranging itself quietly above our heads, twice a day, forever, whether or not anyone below happens to be tuning a radio dial to notice. There's a wonderful, slightly eccentric human detail that belongs right here, folded in gently rather than turned into some long detour, because it fits so naturally into this particular scale of sky and magnetic field and glowing gas. A Norwegian scientist named Christian Birkeland, working in the very early 1900s, became fascinated by the aurora and set out to recreate it, in miniature, inside his own laboratory. He built what he called a Terrella, a small magnetized sphere meant to stand in for the Earth, and he suspended it inside a vacuum chamber, and he fired streams of charged particles at it, watching, delighted, as those particles curved and funneled toward the poles of his little metal sphere in exactly the pattern you'd expect if his theory about the real aurora was correct. Picture that for a second, a man in a chilly laboratory in Norway, more than a century ago, building a tiny model Earth out of metal and magnets, trying to conjure a miniature version of the Northern Lights right there on his own workbench, essentially trying to build a tiny planet in a jar to test an idea about the actual sky. It's a strange and rather touching image, that impulse to shrink something as vast as the aurora down to the size of a benchtop experiment, just to hold it close enough to understand. It's worth noticing, too, that this isn't a phenomenon unique to our own planet, tucked away as some special, private feature of Earth alone. Any planet with both a magnetic field and some kind of atmosphere ends up hosting some version of the same show. Jupiter has auroras far more powerful than Earth's own, glowing steadily around its poles, fed partly by the sun and partly by material flung out from its own volcanic moon. Saturn has them too, rippling around its poles in ultraviolet light invisible to human eyes, but perfectly visible to the right instruments. It's a nice thing to realize, gently, that this shifting curtain of glowing plasma isn't a one-time gift given only to this one small planet, but something closer to a universal consequence, playing out quietly around any world with the right kind of magnetic shield and the right kind of thin, breathable air wrapped around it. If you're feeling your attention loosen and blur a little right now, that's the right place to be, because there's nothing sharp or demanding left in this part of the sky. Just a green and violet curtain swaying overhead, and a man in a cold room 100 years ago, hunched over a tiny magnetized globe, trying to catch the same light in a bottle. Because here's the thing worth carrying forward as we get ready to pull back even further. Everything we've talked about so far, the candle flame, the lightning bolt, the aurora rippling across the Arctic sky, all of it has depended, one way or another, on the sun. The sun's ultraviolet light creating the ionosphere. The sun's constant stream of particles feeding the aurora. Even, indirectly, the heat that lights a candle traces back to sunlight stored in plants a very long time ago. So it feels almost inevitable now, doesn't it, that our next stop, as we keep pulling back and back, has to be the sun itself, because everything we've encountered on the way up here has been, in one way or another, its shadow, its echo, its influence reaching down toward the ground. Let's go meet the source directly. So let's pull back out past the ionosphere, out past the last thin wisps of atmosphere, out into the true emptiness of space, and let's keep going, past the moon, out across that huge quiet gap of roughly 150 million kilometers, until we arrive at the sun itself, sitting there, enormous and blinding, the way it has for about 4.5 billion years, and the way it will keep sitting there for several billion more. Here's something worth turning over slowly, because it's easy to say quickly and much harder to really absorb. The sun is not solid. It is not liquid. It has no surface in the way a planet has a surface, no ground you could stand on even in principle, no matter how much you might have pictured it that way as a kid, looking at drawings of a smiling yellow ball. The sun, from its core all the way out to its faint, wispy outer atmosphere, is almost entirely plasma. The exact same phenomenon we've been following this whole time, from the candle flame to the lightning bolt to the shifting curtain of the aurora, except here it isn't a thin, delicate wisp of the stuff clinging to the top of a thunderstorm or the tip of a mast. Here it is the entire object, from end to end, an enormous sphere of ionized gas, held together not by any solid structure at all, but purely by its own tremendous gravity, pulling all that plasma inward against its own desire to expand and drift apart. At the very center of the sun, deep down in a core roughly 250,000 kilometers beneath what we casually call its surface, the pressure and temperature are so extreme, something like 15 million degrees, that hydrogen atoms are being crushed together with enough force to fuse into helium, releasing an almost unimaginable quantity of energy in the process. That's fusion. In its plainest possible terms, hydrogen becoming helium, a tiny bit of mass converting into a tremendous amount of energy, And that energy is what eventually works its way outward, through layer after layer of the sun's interior, over tens of thousands of years actually, bouncing and scattering and slowly diffusing outward before it finally escapes as the sunlight that reaches your face on a warm afternoon. A journey so slow that the light warming your skin today began its trip toward the surface long before you were born. We're not going to get lost in the mechanics of how that fusion actually works, the specific chain of nuclear reactions involved, because that's its own whole engineering story for another night. What matters for us right now is simpler and more visual. The sun is a plasma object, held in a shape only by its own gravity, generating its light and heat through fusion happening deep in its core, and everything we can actually see of it, from its glowing visible disk to the faint pale halo that surrounds it, is plasma, behaving collectively, the electrons and ions all wired together electrically and magnetically in ways ordinary neutral matter never is. If you've ever seen a photograph of the sun's visible surface, that layer astronomers call the photosphere, you might have noticed it isn't actually smooth or uniform. It's covered in a fine, mottled, granular texture, and scattered across it are darker patches called sunspots, cooler regions where the sun's powerful magnetic field is so tangled and intense that it actually suppresses the flow of hot plasma rising up from below, leaving that particular patch a little cooler and a little darker than the plasma surrounding it, though even a sunspot, cooler as it is, would still be blindingly, lethally bright if you saw it up close on its own. And arcing up out of the sun's surface, especially near those active, tangled sunspot regions, you sometimes get coronal loops, enormous glowing arches of plasma tracing out the shape of the sun's magnetic field lines, sometimes stretching for distances larger than the entire Earth, hanging there in graceful, luminous curves before eventually collapsing back down or erupting outward entirely. And then there's the strangest, most genuinely puzzling thing about the sun, something that still doesn't have a fully settled explanation even now, which makes it a rather nice thing to sit with in the dark, unresolved, the way a good mystery should sometimes be allowed to stay unresolved rather than immediately tidied up. The sun's visible surface, that photosphere we just talked about, sits at around 6,000 degrees. Reasonable enough, hot beyond anything you could ever survive touching, but at least it fits the pattern you'd expect, hottest at the core, gradually cooling as you move outward toward the edge. Except then you get to the corona, that faint, wispy outer atmosphere of the sun, the pale halo you can only really see with your own eyes during a total solar eclipse, when the moon blots out the blinding disk and lets that delicate outer glow become visible. And the corona is not cooler than the surface below it. It is dramatically, bafflingly hotter, sometimes reaching 1,000,000 degrees or more, hundreds of times hotter than the visible surface sitting directly beneath it. Just sit with that for a second, without needing to resolve it, because plenty of very smart astrophysicists have spent entire careers on this exact puzzle without fully resolving it either. Move away from a heat source, and things should get cooler, the same way a room gets colder the farther you walk from a fireplace. But the sun's atmosphere breaks that expectation completely, growing hundreds of times hotter as you move further from its surface, out into that thin, ghostly corona. There are theories involving magnetic fields braiding and snapping and releasing bursts of energy the way a rubber band releases energy when it's twisted too far and lets go. And there's real observational evidence supporting pieces of those theories, but the full picture still isn't completely nailed down. It's one of those lovely, honest gaps in human understanding, a genuine, unsolved mystery sitting right there in our own solar system's front yard, in the star we orbit every single day of our lives, still holding a little bit of its mechanism back from us. So there's the sun, then, an entire object made almost entirely of plasma, shaped only by its own gravity, its surface mottled with granules and sunspots, its outer atmosphere arching with glowing magnetic loops, its corona inexplicably, mysteriously hotter than the bright surface sitting just beneath it. It's easy to look at a photograph of the sun and see a smooth, static yellow circle, the same reassuring image you drew as a kid with a box of crayons, and completely miss just how wild and turbulent and electrically alive the actual object is, moment to moment, second to second, an enormous restless sphere of charged, glowing gas that never once sits still. All of this activity, the sunspots, the coronal loops, the sudden bright flares that occasionally erupt from those tangled magnetic regions, rises and falls in a long, slow rhythm called the solar cycle, roughly 11 years from one quiet minimum to the next, the sun's surface growing more freckled with sunspots and more prone to eruption for a few years, then calming again, then building back up. Nobody watching the sun on any single ordinary afternoon would necessarily notice this slow underlying pulse, the way you wouldn't necessarily notice a person's heartbeat just by glancing at them once. But it's there, steady and recurring, humming along beneath the surface of every quieter day-to-day flicker and shimmer. And every so often, during that quiet handful of minutes when the moon slides directly in front of the sun's blinding disk during a total eclipse, people gathered on the ground get to see all of this laid bare at once. The pale ghostly corona suddenly visible around the darkened disk, sometimes with a bright loop or a streamer of plasma clearly hanging there in the sky. A sight so startling that historical accounts from centuries past often describe entire crowds falling into hushed silence. Before dawn, choruses of birds went quiet, before anyone had any real physical explanation for what was actually happening above them. If your thoughts are starting to blur again around the edges, let them. There's nothing more to hold on to right here except heat and light and one lovely unresolved mystery hanging in the sun's outer atmosphere. Because here's the thing, and it's worth carrying forward gently as we get ready to keep pulling back. The sun doesn't just sit there quietly, radiating its light out into empty space and otherwise minding its own business. It's constantly breathing outward, exhaling a steady stream of its own plasma in every direction, all the time. And that exhalation reaches so far, inflates such an enormous, invisible bubble around the entire solar system, that it's going to take us a good long while, at the scale we're about to move into, just to reach its outer edge. So let's pull back again, out past the sun's blinding disk, out past the orbit of the innermost planets, out past Earth itself and Mars and the gas giants further out, because the sun's influence doesn't actually stop at its own visible edge. It keeps going, invisibly, in the form of that constant exhalation we just mentioned, a steady outward stream of charged particles called the solar wind, flowing outward in every direction at speeds of several hundred kilometers every single second, filling the space between every planet in this solar system, all the time, whether anyone happens to be paying attention to it or not. That constant outward breath of plasma inflates an absolutely enormous bubble around the entire solar system, a region called the heliosphere. And it's worth just letting the scale of that word settle for a moment, because we're no longer just talking about the sun itself, or even the handful of planets orbiting it. We're talking about a bubble of the sun's own outward flowing plasma, stretching so far out into space that it swallows every planet, every moon, every asteroid, everything we've ever sent a spacecraft to, and keeps going for a very long way past all of that before it finally starts to run out of momentum, pushing up against the thin, faint plasma that fills the space between the stars. It helps, maybe, to have some feel for just how large this bubble actually is, even though numbers like this tend to slide right past the mind rather than settling into it. Light itself, the fastest thing there is, takes light only about 8 minutes to cross the gap between the sun and the Earth, and yet it takes that same light something like a day and a half just to reach the outer edge of this heliosphere bubble we're currently floating through, still well within the sun's own breath, still nowhere near truly interstellar space. A day and a half, at the speed of light, just to reach the edge of one star's exhaled bubble. It's the kind of number that isn't really meant to be calculated so much as simply felt, the way you might feel the size of a cathedral ceiling without ever measuring it, just by standing underneath it and letting your neck tilt back further than it usually needs to. There's a wonderful, vivid, almost frightening moment in history that belongs right here, a story about what happens when this vast, usually gentle exhalation of the sun suddenly hiccups, and it's worth slowing down for because it's a genuinely striking scene, even though we're only going to spend a little while with it before we keep moving. In early September of 1859, astronomers noticed an enormous flare erupt on the surface of the sun, and not long afterward, the Earth was struck by a tremendous surge of charged solar material, an event now called the Carrington Event, named after one of the astronomers who observed the original flare. That surge slammed into Earth's magnetic field with such force that telegraph systems all across Europe and North America, the entire cutting-edge communication network of the era, went haywire. Telegraph wires sparked and threw off actual visible flames in some offices. Operators reported receiving messages even after they disconnected their batteries entirely. The induced electrical current in the long telegraph lines apparently strong enough to carry signals all on its own. And the aurora, that shimmering curtain we spent time with a little while ago, was seen far outside its usual Arctic range that night, glowing so brightly and so far south that people in Cuba and in other tropical regions that almost never see the northern lights looked up and saw the sky itself blazing with color, some of them reportedly convinced the end of the world had arrived. It's a lovely, eerie scene to picture for a moment. Telegraph operators startled by wires sparking on their own in the middle of the night. People far from the poles looking up in wonder and fear at a sky, doing something it almost never does. All of it caused by a sudden violent gust in this vast, usually gentle solar wind we're currently drifting through. It's worth noting, gently, that a solar storm of similar strength happening today would likely cause far more serious disruption than it did in 1859. Given how much more of daily life now depends on electrical grids and satellites, and the kind of infrastructure that simply didn't exist back then. But we don't need to dwell on that thought for too long tonight. It's just worth having brushed past it, the way you might notice a warning sign on a quiet road without needing to stop and read every word of it. As we keep drifting outward, past the orbit of the farthest planets, past where any planet at all still orbits, we eventually reach the objects that have traveled further from home than anything else humanity has ever built. Two small spacecraft, Voyager 1 and Voyager 2, launched all the way back in 1977, originally meant to study Jupiter and Saturn and their moons, a mission that succeeded so completely and so far beyond expectations that both spacecraft simply kept going afterward, drifting ever further outward, sending back a faint trickle of data across a gap that grows more vast with every passing year. And it was these two small, aging, impossibly distant machines that finally gave humanity its first direct measurements of the true edge of the heliosphere, the boundary called the heliopause, where the sun's outward-flowing plasma finally runs out of momentum and gives way to the thin, cold, different plasma that fills the space between the stars. Voyager 1 crossed that boundary in 2012, and Voyager 2 followed in 2018, each one detecting, from its own instruments, a sudden, unmistakable change in the character of the plasma surrounding it, the density and behavior of the particles shifting in exactly the way you'd expect at a genuine boundary between two different regions of space. Sit with that for just a moment, gently, because it's a strange and rather moving image to hold in your mind as you drift towards sleep. Two small machines, each not much bigger than a car, launched by human beings back in the 1970s, still faintly humming along on decades-old power sources, have only just now, in the scope of a whole human lifetime, finally slipped past the edge of the sun's own breath and out into the space between stars, becoming the first things we've ever built to leave the bubble entirely. There's something worth noticing here, too, about how strange and enormous this particular scale actually is, compared to everything we've walked through so far tonight. It's taken these two spacecraft, traveling faster than almost anything else humans have ever launched, well over 40 years just to reach the edge of this bubble that still, in the grand accounting of everything left to come tonight, counts as being fairly close to home. We are still, at this exact moment in the story, only just leaving our own sun's exhaled breath. Everything past this point belongs to a different neighborhood entirely. For a long time, nobody was entirely sure this outward breath even existed at all, and it's worth folding in, gently, the small story of how that changed. Back in the 1950s, a physicist named Eugene Parker proposed, on paper, using nothing but careful mathematics, that the sun's outer atmosphere simply couldn't stay still, that the extreme heat of the corona would force it to expand outward continuously, streaming across the whole solar system rather than just sitting quietly around the sun the way earlier scientists had assumed. Plenty of his colleagues were skeptical at first, reluctant to accept the idea of a star that never stopped exhaling. Spacecraft measurements taken not long afterward confirmed he had been right all along. An outward stream of plasma flowing continuously in every direction, exactly as his equations had predicted, and that vast bubble it inflates now carries his name in one of its features, a boundary partway out called the termination shock, where the solar wind, having pushed outward for billions of kilometers, finally slows down abruptly as it starts to feel the faint resistance of the interstellar plasma, waiting beyond it. Well, before it ever reaches that final heliopause boundary the two Voyagers eventually crossed. If your thoughts are drifting loose again, that's exactly where they should be, floating somewhere out past the edge of a bubble that took 40 years and two faithful little spacecraft to finally reach. There's nothing left to hold on to here except the faint hum of old machinery, farther from home than anything else humanity has ever built, still sending back its quiet signal across a gap that keeps growing every single year. Let's keep drifting outward now, past even that faint boundary, out into the thin, cold, mostly empty space between the stars themselves, because there's a whole different kind of plasma waiting for us out there, quieter and stranger than anything we've encountered yet. Out here, in the space between stars, everything gets quieter and thinner and much, much slower to cross, and it's worth letting the sheer emptiness of the distances involved settle in gently before we go any further. Even the very nearest star to our own sun sits so far away that light, again the fastest thing there is, needs more than 4 years just to travel the gap between the two, which means the thin haze of interstellar plasma we're about to drift through isn't just some narrow gap between neighboring houses on a street. It's an ocean, mostly empty, mostly dark, with stars scattered through it the way a handful of lit windows might be scattered across an entire darkened countryside at night, each one a tiny, warm point of light separated from its neighbors by an almost incomprehensible stretch of quiet, mostly empty distance. But it is not actually empty. Not in the way people sometimes imagine when they picture the gaps between stars as simple, total nothingness. Scattered thinly through that darkness is a faint, diffuse haze of interstellar plasma, atoms and ions and free electrons drifting at almost unimaginably low densities, sometimes just a single particle in a space the size of a large room, and yet still behaving, even at that extreme dilution, according to the exact same electrical and magnetic rules we've been following all night. It's the same phenomenon we met inside a candle flame, the same phenomenon that lit up the sky above Cuba in 1859, just spread out so thinly now, across such an enormous volume of space, that it barely deserves to be called a haze at all, more like the ghost of one. And scattered through that thin, dark, mostly quiet expanse, every so often, you come across places where the plasma gathers itself into something dense enough to actually glow, visibly, gorgeously, against the blackness surrounding it. Nebulae. Enormous, softly luminous clouds of gas and plasma, lit up from within or from nearby, by the fierce ultraviolet light of young, hot stars forming somewhere inside or near them. The same basic ionization story we've followed all night, sunlight, or starlight in this case, stripping electrons loose from atoms, leaving behind a glowing, structured, endlessly beautiful cloud that can stretch across distances so vast that light itself takes years or centuries just to cross from one edge to the other. Photographs of nebulae tend to get processed into impossibly vivid colors, reds and blues and pale golds. And while the true colors as your own I would actually perceive them are usually far more subtle and muted than those enhanced photographs suggest, the underlying reality is no less remarkable for being quieter than the pictures make it look. These are genuinely some of the most visually stunning objects in the entire sky, vast slow-moving clouds of glowing plasma, sculpted by starlight and gravity into shapes that linger in the dark for spans of time that make an entire human lifetime look almost impossibly brief by comparison. Some of these glowing clouds are places where new stars are actively being born, dense knots of gas slowly collapsing under their own gravity, growing hotter and denser at their centers until, eventually, deep inside that collapsing knot, the pressure and temperature climb high enough to ignite fusion and a new star flickers into existence, lighting up the very cloud that gave birth to it from the inside out. Others glow not because they're forging anything new within themselves, but simply because they happen to be sitting near an already existing bright star, catching and scattering its light the way a fine mist catches and scatters the beam of a flashlight on a damp night. Either way, the underlying substance doing all that catching and glowing and scattering is the same ionized gas we've been following the whole night through, dressed up here in some of its most patient and most visually stunning clothing. This is a nice place, actually, to just slow down and let the pace of the words themselves loosen a little, because there's nothing urgent happening out here, nothing sharp or demanding, just enormous, patient clouds of glowing gas, drifting almost imperceptibly across timescales too long to really picture. And if you're feeling your own thoughts drift along with them right now, softening at the edges, losing their grip on any particular thread, that's exactly the right way to be moving through this part of the night. There's nothing you need to hold on to tightly here, just soft light and slow time, and a kind of hush that settles over everything once you get far enough from any single star. Out here, too, scattered among the ordinary stars and their gentle glowing nebulae, are a few far stranger, far more extreme objects, worth mentioning briefly, in that same hushed, unhurried tone rather than as some jarring, dramatic interruption. Pulsars, the collapsed remnants left behind after a massive star's core implodes, spinning impossibly fast, sometimes hundreds of times every single second, sweeping a narrow beam of radiation around like a lighthouse, so that from Earth we perceive it as a rapid, perfectly regular pulse of light. And magnetars, close relatives of pulsars, wrapped in magnetic fields so ferociously strong that they're almost impossible to describe in any way that feels intuitive, fields trillions of times stronger than the one generated deep inside our own planet. Both of these are extreme plasma environments, matter behaving in conditions so far beyond anything we experience here that the ordinary rules start bending in strange directions, and it's fine, right now, to just let them exist in this story as distant, exotic, half-glimpsed shapes out there in the dark, rather than as something we need to fully unpack and explain. Some things are better held loosely, appreciated for their strangeness, without needing to be pinned down completely before we move on. So here we are, drifting through this quiet, thin, mostly dark expanse between the stars, past softly glowing nebulae, past the strange distant lighthouse flicker of pulsars, past magnetic fields so intense they barely make sense on paper, let alone in the imagination. And still, even out here, so far from any single sun, so far from any single planet, the same underlying phenomenon keeps showing up, the same story we started with, tucked inside the smallest imaginable atom, playing itself out again and again at every single scale we've visited tonight. Let's keep pulling back a little further still, because there's one more scale left to reach, the largest one there is, and it's going to bring us, in a strange and rather beautiful way, right back around to where every single atom in your own body actually came from. So let's take the final outward step tonight, the biggest one there is, pulling back not just past our own galaxy now, but past countless other galaxies as well, out to a scale so enormous that individual galaxies themselves start to look less like separate, distinct islands, and more like scattered grains of light caught inside something larger, some vast, faint, threaded structure that stretches across the entire observable universe. Scientists call it the cosmic web, and it really does look something like a web, or maybe something like the delicate structure of foam, great long filaments of galaxies strung together across unimaginable distances, wrapped around enormous, mostly empty voids, the whole pattern looking, in the computer simulations that map it out, remarkably like a vast, slow-motion lattice of soap bubbles, stretched across the darkness on a scale that makes even the heliosphere we drifted past earlier tonight feel almost embarrassingly small by comparison. And laced all through that cosmic web, filling the enormous, mostly empty gaps between galaxies and clusters of galaxies, is yet another form of plasma, this one so thin, so hot, and so diffuse that it goes by its own particular name among astronomers, the warm-hot intergalactic medium, sometimes shortened to a phrase that sounds almost too playful for something so vast. It's not glowing brightly the way a nebula does, not visible to the eye even with a very good telescope, but it's there, extremely hot, extremely sparse, threading itself along the same filaments that the galaxies themselves are strung along, the largest and least visible structure in the entire visible universe. And it is, again, plasma. The same fundamental phenomenon we met inside a candle flame at the very start of tonight, just stretched out now across a scale that genuinely resists being pictured in any ordinary, intuitive way. And it's right here, at this largest of all possible scales, and only right here, that we're finally going to loop back to the very beginning of everything. Because this vast cosmic web of galaxies and thin, hot plasma threading between them is not simply a structure that has always existed in its current form. It grew slowly, over billions of years, out of something far stranger and far more uniform, an era so early, so far back in time, that it takes us all the way to the first few 100,000 years after the beginning of the universe itself. Here's what that era was actually like, as best as physicists have been able to reconstruct it. In the earliest stretch of the universe's existence, everything, every single bit of matter that would eventually become every star and every planet and every atom in your own body, was compressed into an unimaginably hot, unimaginably dense state. And under those conditions, matter simply could not exist as ordinary neutral atoms at all. It was far too hot for that. Electrons could not settle into stable orbits around nuclei, because any electron that tried was almost instantly knocked loose again by the sheer surrounding heat and energy, over and over, endlessly, before it ever had a chance to settle down. So instead, for the first roughly 380,000 years of the universe's existence, everything that existed anywhere, all the matter that would eventually make up everything you have ever seen or touched or been, existed as one single, enormous, unbroken, glowing plasma. Not a candle flame's worth, not a sun's worth, not even a galaxy's worth. The entire universe, in its earliest infancy, was plasma, and only plasma, from edge to edge, everywhere, all at once. And because that early universe was entirely plasma, it was also entirely opaque, in a very particular and important sense. Light, in the form of photons, could not travel freely through that early plasma the way light travels freely through empty space today. It kept scattering, bouncing constantly off all those free, loose electrons filling the universe, the way light scatters and diffuses inside a thick fog, unable to travel in a straight line for any meaningful distance before being knocked off course again. The whole universe, in its plasma infancy, was essentially fogged in, glowing brightly but impenetrable, light trapped and scattered everywhere, unable to escape in a straight line to anywhere at all. Then, after those first roughly 380,000 years, as the universe kept expanding and, in expanding, kept cooling, it finally reached a temperature low enough that something remarkable became possible for the very first time. Electrons could finally settle into stable orbits around nuclei without immediately getting knocked loose again. Neutral atoms, for the first time in the history of the universe, actually began to form and to stick everywhere, all at once, an event physicists call recombination, even though it's really more of a first combination, since those electrons and nuclei had never actually been bound together before that moment in the first place. And the instant that happened, the instant all that plasma settled down into ordinary neutral gas, the fog lifted. Suddenly, for the first time in the universe's existence, light could travel freely, in straight lines, without constantly scattering off loose electrons, and that first burst of light, released the very moment the universe stopped being plasma and became transparent, has been traveling outward, in every direction, completely unimpeded, ever since. It's still out there right now, this very moment, stretched and cooled by billions of years of the universe's continued expansion into a faint, extremely uniform glow of microwave radiation that fills the entire sky in every single direction you could possibly point a sensitive enough instrument. Astronomers call it the cosmic microwave background, and it is, quite literally, the afterglow of the universe's own plasma phase, the leftover light from the exact moment the whole universe stopped being a single unbroken sea of ionized particles and became, instead, the beginning of everything we'd eventually recognize as ordinary matter. There's a small, almost funny human story tucked into how we actually found that ancient afterglow, worth folding in gently right here. Back in the 1960s, two radio engineers in New Jersey, Arno Penzias and Robert Wilson, were working with a large, sensitive antenna, trying to track down the source of a faint, persistent hiss of radio noise that kept showing up no matter which direction they pointed the thing. They cleaned the antenna thoroughly, certain the noise had to be coming from something mundane, and at one point even found a pair of pigeons nesting inside it, leaving behind what they later politely described in a paper as a white dielectric material, and they cleared that out too, hoping that would finally solve it. The hiss remained anyway, steady, uniform, coming from every direction in the sky equally, and it turned out, once other physicists nearby heard about it, that what they'd stumbled onto completely by accident, while trying to fix what they assumed was a technical nuisance, was this very afterglow, the actual leftover light from the universe's ancient plasma phase, still humming quietly in every direction, everywhere, all the time. Sit with that for just a moment, gently, because it's worth letting the full shape of it settle rather than rushing past it. Every single atom that has ever existed anywhere, every atom in every star, every atom in every planet, every atom in your own body lying there right now, spent its very earliest infancy as part of one enormous, single, unbroken plasma, filling the entire universe, glowing and opaque and scattering light in every direction for those first few 100,000 years before it ever became anything else at all. Plasma isn't some rare, exotic state of matter that only shows up occasionally, in a candle flame here, a lightning bolt there, a distant nebula somewhere else. Plasma is where everything started. It is, in the truest and most literal sense available to us, the universe's original, default condition, the state every single particle of ordinary matter passed through before it ever cooled down enough to become anything else at all. And this means that solids and liquids, and the ordinary gas you're breathing right now as you lie there, the states of matter that feel so permanent and so obviously normal to us, the ones we build our entire everyday sense of the physical world around, are actually the strange, late-arriving exception, not the rule. They only exist at all because, on this one small, cool, quiet planet, temperatures happen to sit low enough, calm enough, for electrons to stay settled into their orbits instead of constantly getting knocked loose the way they were during that first fiery age of the universe, or the way they still are, right now, inside the sun, inside a lightning bolt, inside the endless hot filaments of the cosmic web stretching between galaxies. We are the exception. This whole cool, solid, liquid, breathable world you're lying in tonight is the strange and rather lucky exception to how matter actually behaves almost everywhere else, across almost the entire history and the entire volume of the universe. If you could somehow shrink the entire observable universe down small enough to hold in two cupped hands, and look at it all at once, this is roughly the shape it would take, not a smooth, even scattering of galaxies like salt shaken evenly across a table, but something far more clumped and threaded, long strands of galaxies gathered together like beads on a piece of string, those strands crossing and knotting together here and there into denser clusters, all of it wrapped around huge, nearly empty voids where hardly any galaxies exist at all, voids so vast that light itself takes hundreds of millions of years just to cross from one side to the other. It's an odd, quiet thing to picture, that the largest pattern in the entire universe looks less like a smooth cloud and more like a spiderweb left out in a garden overnight, dew gathered along its threads, catching whatever faint light happens to reach it. It's worth mentioning, gently, that this enormous web-like structure didn't assemble itself out of pure randomness, out of gas and plasma, just happening to clump together here and there by chance. There's an invisible scaffolding involved, an unseen form of matter that doesn't glow or scatter light the way ordinary plasma does, one that outweighs all the ordinary visible matter in the universe several times over, and its gravity is what first pulled thin strands of gas together into the long filaments the galaxies would later gather along. The way an invisible wire frame might guide the shape of a sculpture before any clay is ever pressed onto it. Nobody has ever seen this scaffolding directly, only inferred its presence from the way galaxies move and cluster in ways that ordinary visible matter alone can't fully account for, and it remains one of the largest and most patient outstanding mysteries in all of cosmology, a hidden hand quietly shaping where all this glowing, structured plasma eventually gathered itself together. This is the largest chamber of tonight's whole journey, the very edge of everything we can meaningfully talk about, and it feels like a good place to just pause here quietly for a moment before we start heading back. Let your thoughts go as loose and as slow as they want to right now, because there's nothing at this scale that needs any sharper focus than a soft, settled awareness that everything, absolutely everything, once glowed together as one single vast plasma, long before there was ever a you, or a planet for you to lie on, or even a single ordinary atom anywhere at all. And now, having gone as far out as there is to go, let's do something we haven't done all night. Let's turn around. Slowly, gently, just once. Because the whole promise of tonight was a single unbroken camera move, out and then, eventually, back, and it feels right, now that we've reached the very edge of everything, to let that same motion carry us home again, quietly, without any rush, retracing the same long, soft arc we've been tracing all along, just in reverse. So we start pulling inward again, away from that vast, threaded cosmic web, away from that ancient afterglow still crossing the sky in every direction, and the first thing that gathers itself back out of that enormous, quiet dark is a single galaxy, one small cluster of light among the countless others scattered along the web, and then, narrowing further still, one particular galaxy among all the others, a broad, softly spinning disk of stars that happens, out near one of its quieter spiral arms, to hold a perfectly ordinary, unremarkable star. Nothing special about this star, nothing that would make it stand out in a survey of a billion others, except that it happens to be the one whose light is warming the room you're lying in right now. On the way back in, drifting past those same soft, glowing nebulae we lingered beside a little while ago, past the same faint, patient lighthouse flicker of some distant pulsar still sweeping its narrow beam around and around, indifferent to the fact that we ever passed by at all, it's worth noticing how unhurried this whole return trip feels, compared to how strange and vast everything seemed on the way out. The cosmic web narrows down into a single galaxy. The galaxy narrows down into a single, ordinary, unremarkable star among billions of others just like it. Nothing out here rushes. Nothing out here needs to arrive anywhere quickly. The whole return journey has exactly the same unhurried, gravity-driven patience that the outward journey had, just running in the opposite direction now, the same way a tide that spent hours going out eventually, just as slowly, comes back in again. Drifting inward past countless other stars and their own quiet nebulae, we find that solar wind again, that same steady outward breath we spent time with earlier, that vast invisible bubble it's been inflating around its own small solar system for billions of years, still pushing outward right now. This very moment, past the same distant point where two small, aging spacecraft only recently managed to slip across its edge. And drifting further inward still, following that outward breath back toward its source, we arrive again at the sun itself, that great restless sphere of plasma, its surface mottled and freckled with granules and sunspots, its outer corona still glowing, still inexplicably hotter than the bright surface just beneath it, that same unresolved mystery still sitting there quietly, unbothered by our visit, exactly the way we left it. Closer now, past the orbit of the outer planets, past Mars, and there, small and blue and easy to miss if you didn't already know exactly where to look, is Earth, wrapped in its own delicate, permanent shell of ionized air, that ionosphere still faithfully bouncing radio signals around the curve of the planet the same way it has every single day since before there was ever anyone alive to send a signal at all. And if the season and the latitude happen to be right, somewhere up near one of the poles, that shifting green and violet curtain might still be rippling quietly across the night sky, entirely indifferent to whether anyone happens to be standing underneath it to watch. Closer again, down through the thinning air, past the altitude where the last stray lightning bolt of some distant storm might still be flickering somewhere over an ocean, its short, violent channel of ionized air already fading, already gone, replaced a moment later by another one somewhere else. The way it always is, somewhere on the planet, every single moment of every single day. And somewhere down near the water, maybe, on some ship none of us will ever see, that same soft hissing glow might be clinging quietly to the tip of a mast again, the way it clung there for sailors centuries ago, still unnamed to whoever might be watching it tonight, still just as comforting and just as strange as it always was, long before anyone had a word like ionization to explain it away. And closer still, down past the clouds, down to the actual sky above the actual house or apartment or room you happen to be resting in tonight, and then in through a window or a wall, or however you want to picture this final approach, down into the room itself, quiet now, dim, holding you and whatever furniture happens to share the space with you. And if there happens to be a candle burning somewhere nearby, or even if there doesn't, just picture one anyway, the way we did at the very start of tonight, that small, warm, flickering orange teardrop of light, doing exactly what it was doing back then, electrons breaking loose and falling back into place, over and over, 100,000 tiny events every second, hidden behind a glow so gentle and so familiar that it never once occurred to you, before tonight, to think of it as the same fundamental thing as a lightning bolt, or the sun's own corona, or the ancient, glowing plasma that filled the entire newborn universe. The same flicker, just scaled down now, by a factor so large it barely makes sense to write out, from the towering, ferocious scale of a star, all the way down to something small enough to sit on a nightstand and throw a soft, warm circle of light across a single quiet room. And closer still, in past the walls, in past whatever curtains or blinds might be drawn against the dark outside, in past the quiet hum of anything electrical still running somewhere in the house, a refrigerator, a fan, a clock ticking on a shelf, all of it built, ultimately, from atoms that share exactly the same distant origin as everything else we've visited tonight, in past the blankets, right down to you, lying there, breathing slowly. And here's the last small step of the whole journey, the one that ties every single scale we visited tonight into one continuous thread rather than a list of separate, disconnected facts. Every single atom in your body, every atom making up your bones and your blood and the breath moving quietly in and out of your chest right now, was, once, an extremely long time ago, part of that very first plasma, that single unbroken glowing sea that filled the entire newborn universe before there was ever a star, or a planet, or a person, or a candle flame anywhere at all. The carbon in you, the oxygen in you, the calcium in your bones, all of it was forged much later, inside the fiery cores of stars that lived and eventually died long before our own sun ever formed. But every single one of those atoms passed through that original plasma state first, back at the very beginning, before any of it had settled down into anything as calm and ordinary as a person resting quietly in a bed. So this is where the whole Zoom actually lands, tonight, at the very end. Plasma is not some rare, exotic thing tucked away in laboratories or hidden behind eclipse shadows or locked inside distant nebulae you'll never actually see with your own eyes. It's the state every single piece of you passed through first, long before you were made of anything solid or liquid or breathable at all. It's flickering gently on your nightstand if there's a candle nearby. It's arcing invisibly overhead every time a distant storm rumbles somewhere over the horizon. It's rippling in green and violet light above the poles of your own planet, right now, whether or not anyone happens to be awake to watch it. It's the sun itself, holding its own shape only through gravity, its outer corona mysteriously hotter than the bright surface just beneath it. It's threaded invisibly all through the vast, quiet dark between every galaxy in the cosmic web. And it's the very first thing the universe ever was, the single unbroken plasma glow that filled everything, everywhere, before there was ever anything else at all. If you're feeling yourself drift now, fully, gently, all the way down, that's exactly where this whole night has been leading. There's nothing left to hold on to and nothing left to remember, just the soft, steady sense that everything around you, the walls of the room, the blankets, the quiet weight of your own body settling into the mattress, all of it is made of atoms that once belonged to a single glowing plasma stretching across the entire newborn universe, long before there was a sun, or a planet, or a bed, or a single quiet room for anyone to rest in at all. That plasma cooled and gathered and drifted and clumped together into stars, and some of those stars lived and died and scattered their own forged atoms back out into the dark, and some of those atoms eventually gathered themselves into a small blue planet. And eventually, after a very long and patient chain of accidents and chemistry, into you, lying here right now, breathing slowly. Made of the exact same original fire that once filled the whole of everything. There's no need to remember any of the specific words we used tonight. None of the names, none of the numbers, none of the particular scales measured out in kilometers or years or degrees. All of that can slip away now, the way it should, the way everything eventually slips away on the way into sleep. What's worth keeping, if anything at all, is just the shape of the whole motion, one long, unhurried breath outward and then back in again, starting inside something smaller than a single letter and ending, somehow, right back here, in a quiet room, with a body breathing slowly under a blanket, made of atoms old enough to have once been part of literally everything. Not just old, present, everywhere, all at once, before there was a single star to gather any of it up into something as calm and specific as a person. So let the room go quiet now. Let the walls fade a little at the edges the way they do right before sleep finally arrives. Somewhere out past the roof, past the sky, past the sun, past the edge of the solar wind's own invisible bubble, past the thin scattered light of every distant nebula. The same story is still unfolding. The same electrons still breaking loose and falling back into place. The same ancient light from the universe's very first plasma still crossing the sky in every direction, quietly, patiently, the way it has for longer than there has ever been anyone around to notice it. And you get to rest now, held together by atoms that were once part of all of that, warmed by a star that is, itself, nothing more and nothing less than an enormous, ordinary, everyday plasma, doing exactly what plasma has always done, since before there was a universe old enough to call anything ordinary at all. Sleep well. The flame is still flickering, gently, wherever you left it, and so is everything else. And if you're still here, still listening, still drifting somewhere between waking and sleep, let one last small image settle over everything else. Somewhere on the night side of this turning planet, right now, a candle is probably burning on someone's table. A lightning bolt is probably cracking somewhere over an ocean. A curtain of green light is probably rippling above one of the poles, and none of them know about each other, and none of them need to, because they were always the same thing underneath, the same quiet flicker, the same electrons letting go and settling back down, playing itself out at every size the universe has ever bothered to build. You don't have to hold on to any of it. You can just rest now, warmed by an ordinary star, made of atoms that once glowed together as one single, ancient light, long before there was anyone here to call it beautiful, or strange, or anything at all.